Welcome to Sundar's lecture. This is lecture number 57, and in this lecture we are going to see TELLEGEN'S theorem. In the previous class we have taken some problems in AC and DC circuits, and we have applied maximum power transfer theorem to find what is the maximum power transferred to the load resistor and what is the resistor that to be connected for maximum power, and so many things we have seen with the examples of AC and DC circuits, right? In this circuit, in this class, we are going to see TELLEGEN'S theorem. See, what is TELLEGEN'S theorem? Before entering into TELLEGEN'S theorem, we try to understand certain things related to power absorbed and power delivered by the electric circuit. And we have seen this one. My previous lecture, I will give you the lecture link in the description. You just go through those lectures, not those lectures, maybe a single lecture, where power balance, we have already discussed about the power balance of an electric network. See, what is power balance in an electric network? Power delivered by the elements should be is equal to summation of power absorbed by the all elements, which means power delivered and power absorbed in an electrical network should be equal, or we can say it in other hand, power delivered, algebraic sum of power delivered and power absorbed should be is equal to 0. So that is the thing we need to understand. See, you take this circuit, we have an voltage source, and you see one thing you have to understand, if current flows from minus to plus in an element, then you can say that that element is delivering power. If current is flowing from plus to minus in an element, then you can obviously say that the power is absorbed by the particular element. That is the whole idea. See, you take this example in this network. See, this I1 current is flowing from minus to plus. So obviously, this is delivering power. This element, maybe this is voltage source here. This is delivering power. And see all other elements. See, this is an element. You don't need to consider it as voltage source or resistor, inductor, capacitor. It may be anything. I have commonly taken this is an element. And what is the voltage across this element? This is plus, this is minus, and this is V2. That's all. And current flowing through that element will be I2. So it is flowing from plus to minus. So obviously this element will absorb power. And if you go for 3, this element number 3, current is flowing in this direction from plus to minus. So it is absorbing power. 4 is absorbing power. 5 is absorbing power. 6 is absorbing power. So if you want to write what is the power balance of an electric network, power balance, we know this one already, we have studied what is power balance. So what I can write here, so power balance V1 into I1 should be is equal to, see, this is only element power delivering and all other elements are receiving power or absorbing power, right? So it will be V2 I2 plus V3 I3, this element, and this element, plus V4 I4 plus V5 I5 plus V6 I6. There are only 6 elements, right? So this equation should be satisfied. This equation should be satisfied. Or in other hands, what I can write, this maybe I will give it a different name, power absorbed. Power absorbed. Maybe I will write like that. So this is delivering and this is absorbing, right? So what I can do here, maybe I just bring this term to the other side. So what happens to this? This is V1 minus of I1 plus V2 I2 plus V3 I3 plus V4 I4 plus V5 I5 plus V6 I6 should be is equal to what? 0. So summation of all the power delivered and power absorbed in an electric network should be 0. I have written it in a way that it is power absorbing. Maybe you just change this current direction in an opposite way, and you can say that this is minus I1, right? For example, if this is the current I1, maybe you change this direction and you put I minus I1, and now this current is flowing from plus to minus. You understand it in that way that minus 1 current is actually absorbing power. Absorbing power. You just try to understand me. See, it may be minus, but this is absorbing power. Minus 2, it is traveling from plus to minus. That is minus 1 current. So I am putting in the absorbed direction. So that this expression should be 0, right? Or you can write it in another way, right? Like power delivered. Power delivered in that expression. What I can do with this expression now, you just bring these element to the left hand side. Everything is like power delivered delivered elements. How will you do that? So this one V1 I1 plus V2 into minus I2 plus V3 into minus I3 plus V4 into minus I4 plus V5 into minus I5 plus V6 into minus I6. This should be also 0, right? This should be also 0. Try to understand what is the power balance in an electric network. Maybe we can say that power delivered should be is equal to power absorbed, or if you say it in a power absorbed direction or power absorbed expression, I have written like that, right? The term I have written it as power absorbed, then this should be satisfied. If I write like power delivered, then this expression should satisfy. That is the whole idea, right? That is the power delivered and power absorbed and power balance in an electric network, right? So you just keep this in mind. This is not Tellegen's theorem. Try to understand this is not an Tellegen's theorem, and we are going to see what is Tellegen's theorem. Let us take a network. See, we have taken a network 1, and in this network, I have assumed the current directions and I have also written the voltages like this, right? This is the first element, second, third, fourth, fifth, sixth elements I have written like this. And now you see what are all the nodes we have here, how many nodes are available. This is node A, this is node B, and this is node C, and you see this one is reference node, reference. You try to understand. We have seen these kind of things already, like nodal voltage analysis method. And now what you do, you just try to write what is the power balance expression here. See, all the elements are receiving power, right? All the elements are absorbing power, since the current direction is from traveling from plus to minus, here also plus to minus, here also I6 is traveling from plus to minus. So every elements, in every elements, current is traveling from plus to minus. Then what is the power balance expression we need to write here? Power balance. Power balance expression. So I'm just I'm just going to write it down as V1 I1 plus V2 I2 plus V3 I3 plus V4 I4 plus V5 I5 plus V6 I6 should be is equal to what? 0. That is the idea, right? So you see in this network, I have just written the power balance expression. And now what you do, take the network number 2. I'm just going to draw the network. See, I have taken the network number 2 and it is the same topology. Let us assume that, and the elements will be different. See, I have written it in a different name. It is V2 dash and I2 dash, I1 dash, V1 dash. Everything I have written with the dash elements, which means the element and the current flowing through the elements and the voltage across the elements will be different from network 1, and you can see that the topology is same. Everything, every topology. See, this is also an element that is connected like this. There is 3 loops and 4 nodes are available in this element, in this network. That is the thing you need to understand here. Anyhow, see, if you take a network like this, I'm going to write the power balance here. Right. So power balance, we will write power balance. Same, right? Here also it will be same. What every currents are flowing from plus to minus in every elements, and it should be like V1 dash I1 dash plus V2 dash I2 dash plus V3 dash I3 dash plus V4 dash I4 dash plus V5 dash I5 dash plus V6 dash I6 dash should be is equal to 0. So this is the power balance expression. For network 1, maybe I will write it as this is number 1 and this is number 2. And we know this. See, until this part, we have not touched what is Tellegen's theorem. See, we have taken two different networks with the same topology and we have written what is the power balance expression. That is what we have done here. And now I will write it down. This is Tellegen's theorem. Try to understand. I have not explained what is Tellegen's theorem yet. I have just told you what is the power balance expression. And what Tellegen's theorem tells us, for example, if you are writing from 1 and 2, I am just writing it down. V1 into I1 dash plus V2 into I2 dash plus V3 into I3 dash plus V4 into I4 dash plus V5 into I5 dash plus V6 into I6 dash should be is equal to 0. See, there is no physical connection, there is no mutual connection between network 1 and network 2. But what Tellegen's theorem explaining us, if you have two different networks and you say elements are different, currents are different, and voltage between the elements are different, everything is a different one. But the voltage in the network 1 into current in the network 2 and then voltage in the network 1, voltage, second voltage, maybe element number 2 voltage, and current in the network 2 in the second element, and if you add up everything, it should be 0. See, there is no physical connection. You cannot signify that these both circuits are connected anywhere else. But how this is possible? And also you can write it down like this. Also, V1 dash in the second network voltage and the first network current plus V2 dash I2 plus V3 dash I3 plus V4 dash I4 plus V5 dash I5 plus V6 dash I6. That should be also 0. See, it is getting interesting, right? Why should this happen? There is no connection. The elements are different. Everything is a different one. But voltage in this network, current in this network, and if you are going to write the power balance, it is coming out to be 0. And that is what Tellegen's explained. So this is the Tellegen's theorem. This is the Tellegen's theorem. And we try to prove what is Tellegen's theorem now, right? What we will do, we will take to the new page, right? See, we have taken the network one and we try to prove now what is Tellegen's theorem. See, this one is valid, right? In the network one, V1 I1 plus V2 I2, every element is receiving power or absorbing power. So I have written like this, right? Power balance expression. And in this, what is V1? What is V1? By you just try to write what is V1 in terms of node voltages. What is V1? The current is traveling in this direction. We have seen these kind of things in the previous lectures, and you try to get what is how to write this node voltages with the voltage of the elements with the help of the elements voltage. And I will give the lecture link in the description. You try to learn how to write what is the node voltages for exact elements, right? So the current is traveling in this direction. So V1 can be written as VA, V1 can be written as VA minus VB into I1, right? That is I1. So plus And then what is V2? See, what is V2? V2, the current, it is only VAO, right? V2, which is nothing but it is VAO. So it is VAO into I2 plus V3. Where is V3? Here it is V3, so it is only VBO. So VBO into I3 plus what is V4? See, V4 is only VCO, right? It is VCO. So VCO into I4 plus what is V5? See, V5 is connected, it is current is traveling in this direction, so VA minus VC, right? So it is VA minus VC into I5 plus V6, where is V6? So it is here, so it is connected between the current is traveling in this direction, so B and C, right? So it will be VB minus VC into I6, that should be is equal to 0. And now you try to get VA element separately, VB element separately, and VC element separately. What is VA element now? So VA into, see, it is I1, right? Plus I1, so I1, and then where is VA element? Again it is here, so it is plus I2, and whereas any yes, here it is a VA element, and it is nothing but it will be multiplied by I5, so it is I5, right? There is nothing, there is no any VA element, so you put plus, try to get what is the VB elements. What is VB element? So in this there is a VB element, and that is minus I1, right? So if you multiply, you will get minus I1, and then VB element, it is I3, so it will be plus I3, and then there are any, yes, yeah, it is I6, right? So it will be plus I6, and then try to get the VC elements. So what is VC element? C, here there is no C, there is no C, here there is a C. See, if VCO or it is VC, I have written it as VCO, anyhow you can write it as VC, maybe to simplify. And what is VC? It is I4, and here it is an VC, that is minus I5, and here it is another one, so it is minus I6, and the whole element on the whole term, that should be is equal to 0. And try to understand one thing, what is this one, what is this one, and what is this one. Try to apply KCL, maybe I will write it down. Apply KCL at node A. At node A, what will you get? See, at node A, if I apply KCL, every currents are going away. All the currents are going away, right? No currents are coming in. So if you put equal to symbol, no currents are coming in. I2, I1, I5 are going away. So it will be I1 plus I2 plus I5. So this is the expression number 1, right? And then apply KCL at node B. What will you get? See, at node B, I1 is coming in, I6 and I3 are going away. So I1 should be is equal to I3 plus I6, or you can write it another way, I1 minus I3 plus, sorry, minus I6. Maybe you bring this one to that side. How can you write this one? So I3 plus I6 minus I1, that should be is equal to 0, and likewise you apply KCL at node C. If you apply KCL at node C, I6 is coming in, I5 is coming in, only I4 is going away, right? So I5 is coming in plus I6 is coming in, I5, I6 is coming in, I4 is going away, so it will be I4. And what you can do, you just bring everything to the other side, so it will be I4 minus I5 minus I6, that should be is equal to 0. This is expression number 2, and this is expression number 3, and try to understand what is this value. This value will be 0, and what is this value? This value I3 minus plus I6 minus I1, this value is 0, and this value is also 0. So everything becomes 0. So this is the whole idea. So this expression will be 0, VA into 0, VB into 0, VC into 0. That should be is equal to 0. So this is the first network, right? So now what you do, you go to the second network, maybe network number 2, And in this network also, what you can do, you just try to write the power balance expression. And I am not going to write it down because whatever we have seen in the network 1 will be also same for the network 2, because every current directions I have written in the same thing, right? So you can directly write, maybe I will write it down, VA into, sorry, VA dashed here, VA dashed here. So what is this one? I1, I2, I5, right? I1, I2, I5. So it will be I1 dashed plus I2 dashed plus I5 dashed plus VB dashed into, what is this one? I minus I1 plus I3, I6. I1, I3, I6 minus I1 dashed plus I3 dashed plus I6 dashed plus VC into, what is VC? I4, I5, I6, right? I4 dashed minus I5 dashed minus I6 dashed should be is equal to 0, right? This is the term we should get. If you apply same thing, you just write down the power balance expression and you convert that V1 into node voltages and everything you do, and you apply KCL also, you will get this term. Apply KCL, this term becomes 0 at A, at B this term becomes 0, at C this term becomes 0. Nothing. KCL at A, node A. Then KCL at B, node B. This one, KCL at node C becomes 0. And what is the thing you have to understand? Whatever the elements it may be connected, whatever the current it may be connected, and these two terms, these node KCL at nodes should be satisfied in every network. Since the topology is same, the current KCL, this current should be 0 and this current also should be 0, right? So now what we can do, obviously we can write down that V1 into I1 dashed plus V2 into I2 dashed plus V3 into I3 dashed plus V4 into I4 dashed plus V5 into I5 dashed plus V6 into I6 dash can be written as 0. Why this is happening? Since the both topologies are same, network 1 topology and network 2 topologies are same, then KCLs at every nodes will be 0. See, I1 dash plus I2 dash plus I5 dash should be is equal to 0, and here also I1 plus I2 plus I5 should be is equal to 0. And that is what Tellegen's theorem explains us. So if you multiply voltage in this network, current in that network, both are 0, right? Anyhow, we have proved that this term is also 0, this term is also 0. And we can write, instead of I1, you can go for I1 dash. You will get all the currents, right? Then if you simplify that, then also KCL at node A, node B, node C becomes 0. That is the whole idea, right? And in other hand, you can write like this also, V1 dashed I1 plus V2 dashed I2 plus V3 dashed I3 plus V4 dashed I4 plus V5 dashed I5 plus V6 dashed I6. That should be is equal to 0. Since you see I1 dashed and I1 should be equal, maybe KCLs at node A, node B, node C becomes 0. So this is actually possible, and this is the Tellegen's theorem. Tellegen's theorem. And this is the proof. Hence we proved it, right? Hence we proved. What is Tellegen's theorem? Tellegen's telling that voltage in a net, if topologies of two networks are same with the different values, power balance, if you take the voltage in network 1 and current in network 2 and power absorbed by all the elements, if you are writing like that, that should be is equal to 0. That is the whole idea, right? You try to look into this intelligence theorem deeply, and we are going to see what is reciprocity theorem in the next class. And in reciprocity theorem, we are going to use or we are going to apply the intelligence. And we are not going to solve any problems with the intelligence theorem, but to know what is reciprocity theorem, and we will solve some problems in reciprocity theorem. And the base of the reciprocity theorem is intelligence theorem. We are going to apply. See this, and you will get an idea. Thank you. We will see in the next class.